Hey, welcome back. In this video I wanted to show you two relatively uncommon setups. One on the lathe, one on the milling machine. For the milling machine I have today a jig grinding setup. On a swap meet I scored this air turbine here. It's this unit. And air turbine spindles are relatively common for ID grinding on certain machines like cylindrical grinders or ID grinding machines, because they reach a ridiculous speed and only need air, but lots of it. And they're very compact, don't overheat, and they have a lot of advantages and a lot of disadvantages. Mainly loud, use a lot of air, and they tend to blow air out to the front and the grinding dust goes everywhere, so I don't overstress this setup currently. And the idea is, this is a special one. This is a Planetary spindle, because the air connector is on this ring here, on a slip ring. Means the machine spindle can turn and the air intake here stays in one position. I have a torque arm here and here in the ring, so I don't wind the hose up because it has some drag due to the seals in this thing. And this is made to fit in a boring head like a Wohlhaupter UPA3, or in my case a Kuroda UFB3. And when I turn on the milling machine, you will see what this thing does. It wobbles all over the place. In fact, what you do with the setup is you replace the boring bar in a boring head with a grinding spindle. That means you can do things like grinding bores in hardened parts, or hard mill bores in hardened parts. You can also put in a carbide burr or a carbide end mill in here. Currently I have an aluminum oxide grinding point in here, and I'm just playing around to grind this bore to dimension. Compared to a regular jig grinder, this is an atrocious setup. A jig grinder has orders of magnitude better machine geometry. This motion, the oscillation, the vertical oscillation of the grinding tool is automated on a jig grinder. The machine spindle, which determines the roundness of the bore, is orders of magnitude better on a jig grinder, obviously, especially in this case with the Optimum MB4 milling machine here. The overhang on a jig grinder is way less because this part here is usually integrated into the spindle of the machine. On a jig grinder, at least on the more number 3 grinders that I have seen, you can adjust the diameter of the bore while the machine is running on a micrometer ring up over the spindle. In this case I have to stop the machine, adjust here and go back down. And about a million other things. Thermal management on a jig grinder. Yes, that's the thing. On a milling machine, not so much. At least not on a milling machine like this. But for the 5 times a year I need to grind a hole or a bore, this might be useful despite the large overhang. And since this milling machine is going away and getting replaced by a Deckel FP1, which is a significant stiffer machine, I have high hopes for this setup to be useful. In reality I bought this spindle for something completely different. If you look at Solid Rock Machining, Steve Barton's YouTube channel, he uses a very similar unit on his surface grinder to do ID grinding. And that's what I really bought it for. This is just a nice additional effect that the spindle has, and also a nice additional ability that I have in the shop now. I haven't checked the RPM yet. It doesn't have a maker sign. I guess it's a Precise or maybe an NSK, not sure. Could be also a fish, could be anything, to be honest. My gut feeling tells me that it's spinning about 50,000 RPM. Haven't checked it yet, but that's my gut feeling comparing it to a die grinder or my NSK hand grinder. This is a metric setup block and it has a through hole, and I'm just grinding the through hole here to size because why not? And I'm aiming for 9 millimeters plus 0.01 millimeters. So let's make some sparks. I will leave the wide shot so you can see the overall operations, and then I will zoom in for close-up detail. So one thing on ID grinding, and probably also chick grinding, I'm obviously no expert on chick grinding, while you're oscillating in the bore and sparking out, you try not to get more than, I think, about half the length of the grinding bit out the bore. Otherwise you will bell mouth the hole, because you have some deflection in the shank of the tool, and that will increase the diameter of the hole the farther you move out. Okay, I think I overshot it. This is a 9mm pin and a 9.01. Doesn't go in all the way. It's a little bit, it's tapered to the bottom of the hole. All these things are something that a gauge pin will tell you. It's between 9 and 9.01, so a band of 10 micron. And the surface finish is serviceable. It's far from good, it's also far from terrible. Let's pull the spindle out of the machine. This is the moment arm. And I have a second moment arm here in the mill. This is usually used for my tapping head. But it used to be the right length for this Planetary spindle. There are other manufacturers. Vise and NSK make electric Planetary spindles with a slip ring like this. Fisher, NSK, and a bunch of others make air spindles like this. And all of them are an emergency solution when you don't have a proper jig grinder. And as you can see, this just drops out of the boring head, and now it's an individual air spindle that I can use somewhere else. For example, over here on my surface grinder, what I can do is I can put my punch grinding fixture here on the end of the table, like this. Move the head all the way over. And put the air spindle somehow mounted to the wheel head like this. Then I can do ID grinding with the table stroke for the oscillation movement. This can be driven by a motor. I can pull the hand crank off and put this pulley for a round belt on here and drive it with the motor. If I put this punch grinding head here on a sine table, I can grind tapers. All I need is a way to mount the air spindle on the grinder like this. This will give me all the options I need for doing ID work. Also, I can grind partial ID and OD radii by using the stops on this punch grinding fixture. Go in here, grind like this, grind a segment of a circle. Here we got the weird setup of the day. I needed to machine a bunch of parts with an eccentric feature on it, and the body of the parts is square. Normal wisdom would be to use a 4-jaw independent chuck, but if you ever have used a 4-jaw independent chuck on very small parts, and especially on a number of small parts, you know that it's an atrocious procedure to set the parts up and not mar them with the jaws when you push the part around in the 4-jaw. Completely terrible. So my first idea was to put the grinding vise on a magnetic chuck and do it that way. Tried it, it worked, but I was limited to about 500 RPM. That put me to sleep. So looking through the items I had here in the shop to cobble something together that works a little bit safer than a magnetic chuck, I found this aluminum faceplate that I cast years and years ago. I just Swiss cheese it if necessary to bolt things to it, and I just machined a slot in the center of it that fits my small 25mm grinding vise. Drilled 2 holes to hold the vise with 2 washers down, and also I put on here a strap clamp as a counterweight to balance it out. And this allows me to use this grinding vise to hold the part. I indicated the part in by sliding the grinding vise lengthwise and by moving the part in the vise sideways. That gives me an XY motion to locate the part. Then I set a stop screw on the side here, which locates the part in this direction. Vise can't move in this direction. And this is the whole setup. This allows me to machine this little boss on the end of this part and drill it. I have the lathe set to 1800 RPM. And as you can see, let's do the old Harding test where I balance a coin on the machine. So here's a coin on the headstock of the machine. I even went up to 2000 RPM here. So that's a very good balanced setup. It's running very, very stable. And this is also very repeatable, since the grinding vise itself is inherently precise, and I have a side stop where I slide my part up against too. So let's machine one of the parts. I cannot show the complete part because customer part, but this outer end should be fine to show. Opening the grinding vise, part goes out. Part goes in like this in the grinding vise. You make sure by sliding it back and forth a minimal amount that it's seated properly. Then you push it up against the stop screw. Second hand reaches for the key. There we go. Change the part. I roughed down this boss on the CNC milling machine because this was an 11mm diameter piece of 14404. Which is 316L stainless. And I didn't want to cut all this down here in the lathe in the setup. I took the CNC mill and just had it whittle away the material with a carbide end mill. But for final finish and precision, I prefer single point cutting with a lathe tool over a mill tool in this case. As you saw, machining on the setup is relatively solid, doesn't do any harm. Keep in mind this is only 2mm in diameter, and the hole I drilled in it is 0.5mm diameter, so 0.25mm wall thickness, and not an issue with the setup to machine this part. In the past I was thinking about putting a self-centering vise on a backplate like this and make it shiftable in XY for things like this. And I even have two self-centering vices, and when I hold it up to the lathe, it looks reasonable. I definitely have to think about this, but I might make something like this just in a little bit better quality. This is a very jank setup that I cobbled together yesterday because I didn't find another way to make this part fast and easy and precise and with a good surface finish on the turn section here. Yes, the finish on the milled part here is atrocious, but that will go away. So I have to retool the setup once again. That's it for these two setups. I hope they were somewhat entertaining and educational. It's probably better to release footage like this in a short format video instead of having it rot away on my hard drive and never see the light of day. So thank you all for watching, and I'll be back.